This video is an introduction to graphing for the Physics 1101-1120 labs. In this video, you'll be learning how to check whether your graph data agrees with a linear theory within uncertainty. You'll also be taught how to make a hand-drawn graph and how to use a program that we have in the labs called Line Graph, which will graph and fit your linear data automatically. So a theory is just an equation that is supposed to describe reality. So this equation describes the displacement of a body moving at a constant velocity. Now, a theory is said to be linear if it follows the pattern y equals mx plus b, the equation of a straight line on a graph. And this theory does, because each of its variables corresponds to one of the variables in y equals mx plus b. So d corresponds to the y variable, and t corresponds to the x variable. Furthermore, each of the constants in this theory also corresponds to one of the constants in y equals mx plus b. So the velocity of the body corresponds to the slope, and the initial displacement corresponds to the y-intercept. Now, when a theory is linear, that means it predicts three things. It predicts that if you plot your variables from the theory on the x and y axes of your graph, that you'll get a straight line graph, that the slope of the graph will be equal to the value predicted by the theory, v in our case, and that the y-intercept will also be equal to the value predicted by the theory, d0 in our case. So what we do in the labs is we take our data experimentally, then we plot it on our graph, we fit a straight line through the data, and then we calculate an experimental value for the slope and the y-intercept, and then you ask yourself, is my data linear with an uncertainty? And I'll explain later in the video how you do that. Then you'll verify whether or not the slope value that you calculated equals the predicted value within its limits of uncertainty. And finally, you check whether your y-intercept equals its predicted value within the limits of uncertainty also. So if you can say yes to those three things, yes, your data was linear with an uncertainty, yes, the slope value equaled the predicted value with an uncertainty, and yes, the y-intercept also equaled its predicted value within uncertainty, then you can say that yes, your data verified this theory. In other words, your data was in keeping with the three predictions made by this theory. Now, before I move on to talking about how you make a hand-drawn graph, I'm going to note that sometimes you want to verify a theory that is nonlinear. So, for example, this theory. This theory governs the swing of a pendulum. So t is the time it takes for one complete back and forth swing of the pendulum, and L is the length of the pendulum. And then we have these constants, 4 pi squared over g, the acceleration due to gravity. So this is a nonlinear relationship. It's t squared versus L. That means if we just plotted our data, we get something that looks like this. So this is a square root relationship. It's not linear, so we can't analyze it very easily. However, there is something we can do, and that's called linearizing the data. So let's compare this theory to y equals mx plus b. Looking at these two equations, we can see that things still kind of line up. The variables are still basically corresponding to the y and x locations in y equals mx plus b, except that we don't have t up here, we've got t squared. So this gives us our means of turning this nonlinear relationship into a linear graph. We'll plot t squared versus L rather than t versus L, because if we do that, then the theory predicts we should get a graph that looks like this, where t squared is on the y-axis, L is on the x-axis, and we get a straight line graph where the slope is equal to 4 pi squared over g, and the y-intercept is predicted to be 0 within the limits of uncertainty. So linearizing the data means plotting a function of the variable on the axes rather than the variable itself, and that's what allows us to take a nonlinear relationship like this and turn it into a linear graph that we can analyze easily. You can orient your graph either this way or this way. What you want is for your data to fill at least half the page in both directions. If it doesn't fit at least half the page, that means you should double your scale. The reason why is that the larger your graph is, the more accurate the slope and y-intercept values you're going to be able to get off of your graph will be. And by the way, you don't need to start at 0, so if your data goes from 30 to 40, for example, go ahead and start at 25. Put your axes right along the edges of the page rather than inset by one block. Remember, bigger is better. Next, you want to choose scales for your axes. And again, you want to fill as much of the page as possible. However, you also don't want to make life difficult for yourself in terms of actually finding decimal values on the scale. So what we recommend is that you choose increments of 1, 2, 4, 5, or 10 to base your scale on, and avoid awkward numbers like 3 or 7. So for example, I've got 4 boxes equals 1 on this axis, and 2 boxes equals 10 on this axis. That'll make it easier for me to find a certain data point on the page. whereas if I had 3 blocks was equal to 1, finding 0.7, for example, would then become quite difficult. Next, you want to label your axes and give your graph an informative title. So your axes labels should consist of the quantity, its symbol, and the units, so time, t, seconds. Your title should be informative, so it shouldn't just be the axes labels again. In fact, I personally will dock marks if students put distance versus time as their title for the graph, because I've already got that information. I want something new in the title. So for your title, either describe the experiment or describe what you're trying to find from your graph. So next you would fill in your data, and I'll just note that obviously I'm putting these down in ink. You are welcome to use pencil for a graph. In fact, we recommend it, because it's so easy to make a mistake when you're trying to put your data down. In order to graph your data, you go in and very accurately figure out where your data point should be located, put a dot there, and then you also want to put in uncertainty bars. So that means if you know that the uncertainty on these measurements are plus or minus 0.25, then you figure out how big 0.25 is on this scale, and you draw it in accurately, plus and minus that amount above and below your data point. And then you do the same thing horizontally. Now the uncertainty bars actually map out an uncertainty box, so an actual box like this that has the same height and width as your uncertainty bars. What you're saying is that the true value, whatever it is, you're confident it's somewhere in this box. Next, you're ready to start drawing your best fit line. So you can either take 2 rulers or 2 pieces of paper and kind of hem in your data. So try and find a region that basically encloses all of the uncertainty boxes within it. It's okay if that's sort of a wedge-shaped area, and it's okay if you kind of cut off the corners of some of the uncertainty boxes, but you want all of your data in this region. Once you're happy with the region that you've chosen, you're going to draw a line straight down the center of it. This is going to be called your best fit line. And I'm going to put my ruler right down the center of that area, and then try and draw my straight line there. So right in the middle of those 2 pieces of paper is where I want to draw my line. Now I'm going to draw 2 more lines on here called the upper and lower bounding lines, but before I would do that, I just want to note that whether or not your graph is linear within uncertainty depends on whether or not this best fit line passes through all of your uncertainty boxes. So you can see that the best fit line is passing through almost all of my uncertainty bars. Is this linear with an uncertainty, however, if this guy falls off the line? Well, yes, actually, because the uncertainty box does touch this line. So as long as the uncertainty boxes all touch or overlap that best fit line, then you can say that yes, your graph is linear with an uncertainty. So you're going to get the slope of your graph off of this best fit line. You're also going to want to find an uncertainty for it, and that's what the upper and lower bounding lines that I'm going to draw in next are for. However, before I complicate things by drawing in more lines, I'll show you how to get your slope from your best fit line. So to get your slope, first you want to choose 2 points that are on the line itself. So not data points, but points on the straight line. So for example, this point and this point. The farther apart they are, the more accurate your slope value is going to be. Now I'm going to label these. So this will be x1, y1, and this one will be x2, y2. So then the slope calculation is one you've probably seen before. Slope is equal to y2 minus y1 over x2 minus x1. So, and I can actually read values off of my graph now. So y2 will be this value, so that's 4.5. y1 will be 1.25. x2 is 95. And x1 is 45. So that gives me 3.25 divided by 50, or 0.0625, pardon me, just made a mistake, 0.065, and you should put units on it. So it's rise over run, so in this case, meters per second. And I'll rewrite that since I made a mistake. So that's how you find the slope of your best fit line. Now, as I said, I'm going to draw 2 more lines in here, and we're going to use that to find an uncertainty for this slope value. So to draw in my bounding lines, I do want this area hemmed in again. In fact, I recommend you draw all 3 of these lines at the same time, rather than stopping and calculating a slope value like I did. So this is the area that contains all of my data, and my 2 bounding lines are just going to go from the top edge over here to the bottom over here, and from the bottom here over to the top here. So I'm going to be making an X across my data. You don't have to be super accurate about this because an uncertainty is an estimate. I'll go roughly from the top here to the bottom down here. And then from the bottom here over to the top on the other end. Now if you do this carefully, all three of your lines should actually pass through the same point. It's not a big deal though, however, because these two extra lines, the bounding lines, are just there to give you an estimate on what the uncertainty of the best fit line's slope is. Next, you would want to choose 2 points on your upper bounding line, that is the steep one, and also your lower bounding line, so the less steep one. So you'd choose a point, say here, and you're going to calculate the slope of this upper bounding line, and also calculate the slope of the lower bounding line. And then, for the uncertainty of the best fit line, which remember is that middle line, your uncertainty would then be, the uncertainty of the best fit line would be equal to 1/2 the difference of the slope of the upper bounding line minus the lower bounding line. So you calculate the slope of these two lines, plug those slopes in here, 1/2 of the difference between them gives you the uncertainty on the center line, the best fit line. Now there's one more quantity that you're going to need to get off your graph, and that's the y-intercept. Now if my x-axis had started at 0, then I could just extend this line back and read off what my y-intercept is. Unfortunately, this graph doesn't start at 0, so I will have to calculate it. So you choose a value on the line itself, and then you plug that into y equals mx plus b, and solve for b. So you could take this x and y value, plug it in here with the slope that you calculated, and solve for your y-intercept. You'll also want an uncertainty on the y-intercept, and again, the uncertainty of the y-intercept for the best fit line would just be 1/2 the difference between the y-intercept of the upper bounding line minus the y-intercept of the lower bounding line. And then the next thing you're going to do is come up with an equation of best fit for your graph. Now to write your equation of best fit, you're going to need the linear theory that the data on your graph is supposed to be governed by, and you're also going to need your experimental values for the slope and the y-intercept of the best fit line, the middle one. So your equation of best fit that you write on your graph is going to look just like this, except that you're going to have actual experimental values for the slope and the y-intercept. So first of all, we put the symbol of what we've got on the y-axis. So you don't put down y, you actually put down d, equals, and now I put in my experimental value for the slope. And by the way, you do need an uncertainty and units, and everything's got to be rounded off correctly. And then it's multiplied by t, the quantity on my x-axis. So I write in t plus, and then I add my y-intercept. And again, this is going to be an experimental value. You have to put in your uncertainty and your units, and everything needs to be rounded off correctly. So that's your equation of best fit, and that has to be written directly on the graph whenever you have a hand-drawn graph or a printout of a graph. So you'll remember that a linear theory predicts 3 things. It predicts, first of all, that you'll get a straight line graph. It predicts what the slope of your graph should be equal to, and it also predicts what your y-intercept is supposed to be equal to. So in analyzing your graph here, you'd say, first of all, is this graph linear with an uncertainty? As I said, the best fit line passed through all of the uncertainty boxes, so yes, this graph is linear with an uncertainty. You'd also want to say whether the slope value you got agreed within its limits of uncertainty with the value that was predicted. And then the third thing that you'd talk about is whether your y-intercept agreed within the limits of uncertainty with its predicted value. So if you can say yes to those 3 questions, yes, the graph was linear with an uncertainty, yes, the slope value equaled the expected value with an uncertainty, and yes, the y-intercept agreed with its expected value with an uncertainty, if you can say yes to those 3 things, then you can say that your graph has confirmed the theory. To find the line graph program, look around on your desktop for a folder that says Physics Spreadsheets, and double-click that to open it up, and then open the most recent version of line graph that you find in there. Now there's a few different versions of line graph in the labs, so depending on which one you've opened up, it could look fancier than this or it might look simpler. So line graph is a program for graphing linear data. We're going to put our data here in this data table, and the program will automatically graph it for us. It'll also calculate the slope and its uncertainty, and also our y-intercept and its uncertainty. So the program's going to do most of the work for us. So as I said, this is your data table. This is where you're going to type in your data. And down here at the bottom, you'll see there's a second tab that says Graph. So if you click on this Graph tab, this is where our data will get graphed. So let me go back to the Data tab now. So I click on the Data tab, and I'm going to type in some fake data now. And I'll also put in uncertainties. And this is a macro of Excel, so you can just use all the same tricks for working with Excel. And you'll notice that these gray columns, if you've got this on your version of line graph, it'll calculate the fractional uncertainty of all your data for you. As I said, this is just Excel, so I'm going to put in a formula here and say that my uncertainty is 2% of the value. So equal sign 0.02 times the value, hit enter, and then I'll copy and paste that formula down. So that's all my data, but I also want to put my labels on here. So there's space for you to put in a title, the x-axis label, the y-axis label, and also you and your partner's names. So I'm going to pretend that this is data for a simple pendulum experiment. So my x-axis would be the length of the pendulum. My y-axis would be the period squared. So period squared, and then the symbol would be t squared. Excel is not as good at putting in superscripts, so I'm just going to use the caret symbol, t squared, and then my units. So again, s caret symbol 2 for seconds squared. Then I'll put in my title. So I'll accept if you just describe the experiment. So for example, the simple pendulum. I'll also accept it if you try to describe what you're trying to get from your graph, determining the acceleration due to gravity. So both of those would be acceptable titles to me. So now if I click on the Graph tab again, it should all be graphed for me. So here's my graph. So it puts in everything except the equation of best fit for you. It does put in these little equations here, but as far as I'm concerned, you can just delete these. They don't have units and they don't have uncertainties on them. But let's go back to this data table again. And I want to point out this second table over here. So table 2. Table 1 is where we put our data. Table 2 is where the program tells you what your slope is and its uncertainty and what your y-intercept is and its uncertainty. So the slope is right here, m best, and the uncertainty is right underneath it. And right beside it is the y-intercept, and underneath that is its uncertainty. So that's all the information we need to write our equation of best fit. So I'm going to go back to the graph now and put in my equation of best fit. Now I'll warn you that inserting an equation into Excel on a graph is not quite as easy as inserting an equation into Word. There's one thing you have to do that's a little different. So to begin with, if you were in Word, you'd go Insert and then Equation, but that's grayed out here on the chart. So you need to do something else first. What you do is you go up here to these Chart Tools tabs, click on Format, and then over here there's an Insert Shapes menu. You want to insert a text box, which is right up in the corner. So I click Insert Text Box, and then I can draw a text box on my graph. So I could just type some text in here. I could go y equals mx plus b, but I actually want to insert an equation here, not just text. So now that I'm inside my text box rather than on the chart, I can actually do that. I can go Insert Equation, and it will allow me to insert an equation. So I'm going to increase the size of the text just so it's easy to see this. And then I'll go back to my Equation Tools tab. And up here you'll see all the menus that should be familiar from using Word to insert equations. So I want to insert my equation of best fit for the graph. So on my y-axis, I've got period squared. So I'm not going to type in y here. I'm going to type in t squared. So I insert a script and I say t squared. Side arrow to get out of the superscript, and then an equal sign. The next thing I'll put in will be my slope, and I'm going to actually put in my experimental value from table 2. For now, I'll just put some brackets there as a placeholder. So that'll be my m, and the next thing I put on there is x. And of course, for this graph, x is length. Next, I go plus, and now I want my y-intercept. And again, I'm going to put in an experimental value for this. So for now, I'll just put in some brackets as a placeholder. So now I'm ready to put in my experimental value for the slope. So for this, I'll need to go back to my data table and actually get the values. So I click on the data table tab and look at table 2 here. And it tells me that my slope is equal to 4.9467 and so on. And my uncertainty is 0.283. So I'll round off my uncertainty first to 0.28. And that means that my value should be rounded off to have 2 decimal places to agree with the 0.28. So that's what I'll put in my equation of best fit. So I click into here, 4.95, and I'll need to click on my equation tools to get those showing up again. Click on plus or minus, and then my uncertainty, 0.28. And now I just need to put in units. So what are the units on the slope? Well, a slope is rise over run, therefore it'll be seconds squared per meter. And finally, I'm going to add my y-intercept. So again, go back to my data table, and the y-intercept is 0.1009, and the uncertainty, once I round it up, is going to be 1.0. So my y-intercept is going to be 0.1 plus or minus 1.0. So I go back to my graph, and I'll type that in. And again, I need units on this. So the y-intercept will have the same units as the y-axis does, seconds squared. So this is my equation of best fit. So that's what you need. So now that I've shown you this, I'm going to show you 2 more tricks for using line graph. So here we are on the data table again. And sometimes you don't want to type in your data by hand because you've already got it in an Excel spreadsheet. So is there a way to copy and paste from your existing spreadsheet into line graph? Yes, there is. Let's say that I had a spreadsheet already made up with all of my data, and I want to now copy and paste this into line graph. I could just highlight it and go copy, and then go into line graph and paste it, but there's actually a better way. You start exactly the same way as what I just showed you. Highlight the data, go up to the copy icon in the clipboard, and then you go into line graph, click where you want it to appear, and instead of going paste, what you're going to do is click the little arrow underneath paste and click on paste link. So I'll show you that again for the y-axis data. You go into your spreadsheet, highlight all your data, go copy, then you go into line graph, click where you want your data to appear, click on the arrow underneath paste, and go paste link. So why do we want to do this? Well, the reason why it's useful is that if you go back to your spreadsheet and realize you made an error somewhere and you want to change your data, so let's say that we change this from 30 to 32, if you change it in your spreadsheet and then go back to line graph, you'll see that line graph has automatically updated. So if I just pasted my values in here, it wouldn't update. So that's what I recommend. So let's go and look at the graph now. I purposefully chose my new data to start above 30, just because I wanted to show you how that would look. The graph automatically starts at 0, and that means sometimes you'll have your data all squished into a little band at the upper end of the chart. So there is a way to make this look less ugly. What you do is you'd right-click on the axis that you want to change, and then select Format Axis. Then I can change what my lower bound is. So I'm going to change this from 0 to 30. When I hit Enter, it fixes my graph for me. When you're happy with how your graph looks, including putting your equation of best fit on, you can save it and then either print it out or hand it in to your lab instructor electronically.